So here's another example of a one sample t-test for means. Teenagers tend to have bad attitudes and roll their eyes. If they are classified as salty if it is proven that they roll their eyes more than 10 times a day. One parent believes they have a salty child. They randomly select 7 days over the course of a year and counted the eye rolls. Is there evidence that the child is salty at a 1% level of significance? All right. So starting lead off, we are going to do our hypothesis statement. Okay. Our null is that the mean equals 10. All right. This is what we're checking. We're trying to figure out if they're salty or not. If they're salty, the mean is going to be greater than 10. So this child averages more than 10 eye rolls a day. All right, so there's our hypothesis statement. Okay, we're checking for if the average number of eye rolls is greater than 10 or not. All right, for our conditions. All right, one, random. It says it in the question that these are randomly selected days. All right, thing number two. We check for, so our sample size is 7. So we do 10 times 7 is 70. Since we're sampling without replacement, we have to assume more than 70 days. Actually, we don't even really need to assume that because they took it over the course of the year. All right. For normality, all right, we can't use central limit theorem because our sample size is not greater than 30. Also, the question says nothing about normality, but we have data points, so we can check a normal plot. All right. So let's go ahead and plug stuff into our calculator. All right. I went stat, edit, and then I put the data set into list one. So the first thing I'm going to do is I want to check for normality. All right. There's a couple of different ways I could do that. I could just look at a box plot and see if it's obviously skewed or not. But the better way to do it is I go into second stat plot. And then this last option right here, this is the normal plot. Okay. So I want to check this. We're looking for a linear like pattern here. So if I do zoom 9, all right, looks pretty good. So we're going to use the normal plot. Make a rough sketch of it. Doesn't need to be anything nice, but just kind of do, there was 1, 2, then you have the vertical stack, 1, 2, 3. Okay, so there you go. The normal plot is approximately linear. So the distribution is approximately normal. All right, so we check all these categories off. So therefore, this is a one sample t-test, okay? So for the name and numbers, this is a one sample t-test for means. All right, as for numbers, let's go to the next page and start looking things up, okay? So just to get these numbers really quickly, I'm just going to go ahead and run this test, all right? When you run a test, it gives you everything that you need to know. So I'm going to go down to t-test. Oh my God, I went right past it. T-test. Oh my goodness. All right. There's data and there's stats. We have data. All right. Mu null. So this is the null hypothesis we're checking against. We are checking against 10. All right. That was our null hypothesis because kids are salty if they're greater than 10. All right. List is L1. This is where our data set is. Frequency is 1. Don't change that. And you're going to go ahead and calculate it. All right. So if you look at this, this gives you a lot of information right here. Okay. So first off, we have a sample mean of 12.1 and a standard deviation of 2.1. All right, our sample size is 7. Let's talk about critical values for a second, okay? So we have a level of significance of 1%. That was given to us in the question. Our degrees of freedom, it's sample size -1, so 6. So to get our tail value that we're looking for, we are looking at 6 degrees of freedom, tail value of 1%. That's our level of significance, and that meets up right here. So we have a critical value of 3.143. So just to kind of give you a little heads up, this is what this is going to look like, okay? So we have a mean of 10, okay? That is our hypothesized value. We believe that the average is 10, okay? Now, here's what we're going to look for. So we also have a t distribution. Our critical value is 3.143. So let's say 3.143. And we know that that corresponded with a tail size of 1%. Basically, this is the number that we have to beat to reject the null hypothesis, all right? So if we get a t-score greater than 3.143, we'll land in the tail, also known as the rejection region, okay? So our t-score, it's the same thing as a z-score is, okay? Mean from the sample divided by mean from the population divided by standard deviation over sample size. So if I plug in my numbers really fast, that's 12.1 minus 10 divided by 2.1 over square root of 7. From our calculator, that gives us a t-score of 2.68. 2.68 puts us out here. All right. So we do not land in the rejection region. Okay. So it's not far enough away from the mean of 10 to say that there is a difference. Okay. It's not statistically significant. We also get a p-value of 0.018. Because our p-value is greater than our alpha, that's a second sign that we're going to fail to reject. Okay. So either way, though, we have our p-value, we have our test statistic. We know what we're going to be doing here. So we know that we are going to fail to reject. So lastly, all we have to do is to come up with our conclusion. Okay. So the conclusion, that is our little 3-sentence wrap up of everything. Okay. So here's what we're going to say. So based on our t-score of 2.68, we fail to reject the null hypothesis. If the number of virals, if the average number of virals were really 10, there is a, what do we say the p-value was? 1.8% chance of getting these results or more extreme, which is greater than our alpha of 5%. Then we do our conclusion. There is not enough evidence to claim that this child is salty. All right, once again, gentle reminder, we never say that the null is true. We just say there isn't enough evidence to prove it false. Okay.